Okay, the next speaker is Promit Mukherjee from Caltech, but the university. Yes. Yeah, and so Promit and here for a month. And so it's a pleasure to introduce him to give a talk on graded homology of groupoid of the higher rank.
Thank you so much. First of all, I'd like to thank Professor Zeroth for inviting me, giving me this opportunity to talk here. It's a workshop. It's a real delight. Okay, so the topic, as Professor Zeroth said, it says that graded zeroth homology of the path groupoid of higher rank graph. But before going to the technical details, I just want to give you an overview of the subject. You can say that the way how I see this subject, what we do or what is usually done in the study of something we call the commutatorial algebras. So whenever you start with the commutatorial object, that may be anything, matrices, graphs, but essentially will lead to some kind of graphs and their variants. So you have a commutatorial object, then you can associate this with some algebras, which we formally call commutatorial algebras. It may be just an algebra, that means the module over a ring with a ring structure itself, and the ring structure and module structure are compatible in some sense. Also, you can put some topology to form sister algebra. So it may be sister algebra or any discrete algebra. So this is commutatorial algebra. The question comes how one can study this commutatorial algebras with the data in hand about commutatorial object. There are many ways to do so. I think the most common line of research, you just associate properties of this object with the algebraic properties of the algebra you have. But if you want to have a very good idea about this algebra, for example, its structure, its very good algebraic properties, then I think it will be really nice if you can associate a third layer that is given by some dynamical systems. So we associate a dynamical system with your commutatorial objects. Definition is like that it's a compact topological space with the kind of homeomorphisms or local homeomorphisms. But how in practical you will get a dynamical system for a commutatorial object? First, you choose a topological space, suitable topological space, and you pick a group or some inverse semigroups. Let it act on your topological space. Then out of that action, you will get this dynamical system. Okay, and then this dynamical system will give you a groupoid. And the best thing is that this groupoid can take care about this dynamics, as well as if you get the groupoid algebra, if you construct the groupoid algebra with the groupoid you have in your hand, then in most of the cases, you will notice that the groupoid algebra will coincide with the algebra you started with on the object. So this you may call a big picture of this whole thing, the study of commutatorial algebra. You have commutatorial objects, you have commutatorial algebra, which you can associate directly. Just get some type of generators and use some relations which are governed by the object you have. But to study this algebra, you can also take this part. First, associate a dynamical system, then consider the associated groupoid. For example, the Deacon-Reynolds model is very good for this. And then the groupoid algebra, this may be a discrete algebra as well as a sister algebra. It will coincide with the commutatorial algebra. Then we call this groupoid a groupoid model for this commutatorial algebra. So this is the big picture. And it comes with a big question also. So suppose you have two objects, two combinatorial objects of the same kind, then can you or how can you tell that the associated algebras are same? So sameness may have different meanings. It may lead to identically same, maybe isomorphism, maybe Morita equivalence, or maybe something else, which I will talk later when I'll introduce the graded setup. Okay, so that's the very basic and natural question in the study of this combinatorial algebras. The one-line answer is like this: associate or try to get some easily computable gadgets from your object, or you can also get this from your algebra, whose sameness can tell you sameness of your algebras. So this type of gadgets, we call them invariants, or more specifically complete invariants. If they have this power, their sameness can tell you the sameness of the algebras you have in it. Right. But the answer, it looks very easy, but it's most of the cases very difficult to find such a nice gadget, right? Okay, since I have some different layers here, for example, algebra, dynamical systems, groupoids, you may talk about invariants in different levels. For example, if you work in the level of algebras, here sameness may have meaning like isomorphism or Morita equivalence. Then it is observed that the K groups may work as those invariants. Right? But let me remind you, or let me make you aware that the computation of these K groups, computations although very challenging. Right. So next, if you work in the level of dynamical systems, then here sameness may have the meaning of conjugacy, or something they call eventual conjugacy. Then there are some invariants available in our hand, for example, the entropy, which captures the complexity of the dynamical systems, the zeta function, some groups like the Bowen-Franz group. These are just partial invariant for conjugacy, and also we have this very good thing for dimensional triples. And last but not the least, if you work at the level of groupoids, then here sameness may have some meaning like isomorphism, because groupoids are obviously categories by birth. So you can obviously talk about their isomorphisms. Equivalence, Morita equivalence, that means the isomorphisms of their G sheets of our modules. Or another thing is their Kakutani equivalence. So all these may refer to the sameness. And then you have this homology and co-homology. So these are abelian groups you associate with your groupoids, which can somehow work as those invariants. Right. So since we want to study this combinatorial algebras from different perspectives, for example, from the viewpoint of dynamical systems or groupoids, it will be very nice if you can connect invariants of different levels, right? So for example, you have this invariant in the level of algebra, so you can connect, if you can connect with the invariant homology in the level of groupoids, then you can say something for this interplay of this algebra cycle. That's right. So today my work is about such a result which connects a group of a certain commutative algebra with the homology of a groupoid made out of the underlying commutative object. So in this regard, I want to mention a result of Matsui, I think in 2012. It says that if G is a groupoid arising from a shift of finite type, something very popular in the world of symbolic dynamics, but you can obviously realize this as from a directed graph is essentially a shift of finite essential directed graphs. So if you have a groupoid which somehow connects with such a shift, then for this type of groupoids, if you form the homology, the zeroth homology, it will be isomorphic with the K group of the corresponding reduced spread. That's a very interesting result which connects invariants at different levels, right? So invariant to the level of groupoids and the invariant to the level of C-square. So an interesting program is that if you have a groupoid, you just want to know that for that groupoid whether this type of isomorphism holds or not. So Matsui proposed some interesting classes of groupoids, for example, all A groupoids with compact unit space falls in this class. So for such groupoids, we observe that the homology coincides with the K. So this is an interesting class. We may get some non-A groupoids which also satisfy this, right? So another interesting program is to get a discrete version of Matsui's result by replacing C-square algebra, which is a topological stuff, with the discrete function, for example, Steinberg algebra. Okay, so today I will talk about one particular such commutable objects which we call the higher rank graphs. I do not know how much of you know about this higher rank graph, so I will give a very basic understanding about this higher rank graphs. And then what we'll do, we'll associate a certain groupoid with this higher rank graphs. And at the same time, this higher rank graphs gives you algebra, which is formally known as the Kuhn-Bosc algebra. You can view this as the higher dimensional generation of your Levitt algebras, constructed from directed graphs. Then we'll see that for this groupoid, the certain groupoid associated with the higher rank of lambda, the graded homology of G lambda coincides with the graded K field of this Kuhn-Bosc algebra. And we prove this by not using any kind of spectral sequences, just using the very basic idea. I will present the sketches of two types of proofs, one using type semigroups and another using just the diagonal subalgebra of state algebra, right? Okay, so before going to that, just let me give you some basic idea about higher rank graphs. You start with the countable small category. Right, that means the class of morphisms is indeed a countable set. If you have counter T from this category lambda to the one object category of the monoid of k tuples of non-negative integers, satisfying a very specific property. Which goes like this. So you take any lambda from your category and plug this functor here, you will get a k tuple of non-negative integers. And if you observe that this k tuple can be written as the sum of two k tuples, then that should imply your lambda, you can decompose this lambda uniquely into two morphisms of your category whose D images of this M&N. So that means there should exist unique mu1, 2 in your category such that lambda is the product of mu1, mu2. D mu1 is M, D mu is. That's the property which is often referred to as the unique factorization property. But this property is very restrictive and very rich in nature that it poses some serious restriction on your K graphs. For example, okay, let me finish this definition. If you have a functor D which satisfies this property, then we call this pair lambda D higher rank graph of rank K, or simply a K graph. So, for example, I can mention about some basic consequences of this property. The first one is that if you take the set of objects of your category, it will coincide with the fiber of zeros. Right. And the next thing which I really like about this higher rank graphs is that there are some type of local cancellation is there. So if you have, so yeah, okay, so second consequence is that if you have lambda mu, let's say lambda mu in your category, then you can easily write mu equals mu. So you can cancel morphisms from left, and at the same time you can cancel from the right. Another interesting fact which follows from this property is that the only invertible arrows are the trivial ones. That means the objects. So this third property makes these K graphs sit at a completely opposite extremity than that of groupoids. In groupoids, what we notice that every arrow is invertible, but here only the trivial ones are invertible. Okay, so this is the thing for K graphs. Before going into some technical details, let me give you some examples. Okay, the most basic one, but the fundamental one is given by any directed graph. So if you have a directed graph, you just consider its path vector. That means objects are the vertices and morphisms are the finite points. With the obvious meaning of source at ranges. And then you can associate this length map from E star to category one object category of natural numbers. Just associate each path to its length. And you can easily check that from the geometry of the graph, it follows that this length functor has this property. So E star lambda is a 1 term. because here we have one. Right. So it's a very basic example, but it lays the foundation of this K things. Second example, I should. Second example is about grid graphs. Right, so you start with again this entity for K, but this time not as a monoid, we are giving this as a poset. Right, with the ordering given coordinates. So then the poset category NK is denoted by, let's say, omega K. I think you're familiar with poset categories. By this, I mean to say the object set is NK, and the morphisms pair of K tuples, so the endless. So this is the poset category. So the poset category is a K graph with this degree factor E omega K to N for K. You take any morphism, that means a pair of K tuples, you send it to a minus. Right. Then you can check that this D also has this unique factorization and you will get K omega. You can replace this poset by any poset you like, and you can do so. For example, you can replace this with CK, for example, or you can also get a finite variant just by taking any particular K tuple and then choose this poset as the downset of N. Right. Principal downset of N. That means in this category, if I denote this by omega Kn, your objects will be this. That means all those K tuples which are less than equal to N. And morphisms will be pair of PQs such that P is less than equal to Q and both are less. And the definition of the degree map will be the same, and then you'll get a finite variant of your of this grid term. I can draw a picture for this. For example, if K is 2 and N is, for example, 2, 1, then omega 2 to 1. You can draw the nodes. Let's start with 0, 0, 1, 0, 0, 1, 1. These are my 6 nodes. Then I will just draw those paths in my picture whose degree, just draw lambda of omega 1 such that degree of lambda is either 0 or 0. For example, this will be an edge directed from 1, 0 to 0, 0, means it has degree 1. Similarly, it has degree 1, 0. This all have degree 1, 0, and the particle ones have degree 0. So you get this finite portion of a grid. Another construction I should mention regard inside this list of examples is the formation of Q program of a K program. So this is a way to produce a new K graph out of a given. So suppose lambda is a K graph. That means you already have this degree map. And then you give this D from a counter from lambda to nk, but nk sits nicely inside the group ck. So you can also view this as a functor from this category to the one object category of this group. Then use these two things to get a big category, which we denote by lambda bar. The object set is lambda naught k. The morphism set is lambda k. Now I'm defining the source in this way. Source of lambda n, that means lambda is a morphism here, n is a k tuple of integers. Defining this as source lambda n plus d lambda. Okay, I'm doing it in a different way as that of Eilers. I think he modified the range. I am modifying the source. And range lambda n. And also if you need a degree map to get a k graph, so define this degree from lambda bar to k lambda n goes to d lambda. So I'm not changing the speed. Then I check that this pair is a k graph, which you call the skew product of your existing k graphs with C. Another interesting construction about this k graphs is the pool vector. You start again with the k graph lambda d. That means you have a functor from lambda with k d, and suppose you have the monoid homomorphism from the monoid of L tuples of non-negative integers to the monoid of elements. So this is just a monoid. So these are all small categories, right? So lambda, nk, nl. So if you consider the collection of or the categories of all small categories, then these are morphisms, these functors. And then just take the pool back, which I denote this way. It's the lambda, essentially is the collection of these pairs, lambda n from lambda cross nl, because the d lambda is same as the. So you have this pullback. Call this the pullback of lambda along F. Then if you define T star from F star lambda n to the power L, simply as lambda n goes to n, then you'll see that this F star lambda to this map is L graph. So this is a common way by which you can change the rank. Right, so you start with a k graph and a monoid homomorphism. Then you can make a L graph. So let's take a basic example to see how this works. So start with this very well-known graph, the rows with one petal. But I am actually taking its path category. So this is a one graph. You can easily realize that the path category is isomorphic with the monoid category of natural numbers. Then first you take the pullback along this monoid homomorphism. Then what do we get? We'll get the skeleton of the two graph, which looks like this. This E is duplicated into a morphism of color 1, 0. The morphism of color is equal 1. And this vertex is this vertex, which we should write this way. So if you have a two graph, then if you take a skew product with Z2, since you have a two graph, then what will you get? You will get this infinite grid, which I have erased that. You'll get the infinite grid. That means the opposite category of C2. This is a very easy example to understand this construction. Now, there are several variants of higher rank graphs, but I usually work in the most simplest case, which called the row finite K graphs without sources, like the row finite directed graphs. I think that's a good place to introduce this vertex matrices of a K graph. So if you have a K graph lambda T, for each of this K tuples in K, you can associate a matrix, find a matrix AN in the collection of matrices indexed by lambda naught. Lambda naught is the Jackson. And entries are coming from non-negative integers in this way. So you set the UVth entry, UV vertices of the K graph, as the number of paths having degree n and property lambda, and such that range lambda is U, source lambda is. So this is the UVth entry of the A matrix. So in this way, you get countably many matrices, but in some sense, you do not bother about so many matrices, just these basic matrices, for example, A1, A2, AK. If you know these matrices, you can build any matrices out of them, because these matrices commute because of the factorization property, and you can write an arbitrary n as simply as A1 in 1 times A2 into A. So we call these the vertex matrices of a K graph. These are really the analog of adjacency matrices. And we call our K graph row finite without sources if each row sum in AN is non-zero and finite. And that should hold for all in. That's an indirect way of defining this, but I feel this is a good place to define these vertex matrices, and also it justifies the name why it is called row finite, right? So we have these matrices, so we'll come to these matrices at the last part of the talk. Okay, now return to the formation of a groupoid with a given K graph. So remember, I initially I said that whenever you have a commutator object, to get a groupoid, you should pass through a layer of dynamical systems, right? So what we'll do, suppose this is a K graph. From now on, all K graphs are row finite without sources. Then we'll first associate a suitable topological space. For that, I think I should define what is called infinite paths. Lambda. So this is not as easy as in the one graph case. In one graph or in directed graph, we all know what is called infinite path, which is just an infinite sequence of concatenable edges. For example, E1, E3, 3, 4, so on. This is an infinite path in your ordinary point graph. But how you can define in this way in a general k-dimensional setting, right? For this, we will realize this infinite path in terms of a certain functor. So realize this. So for example, let this infinite path be called P. Realize there's a certain function mu P from the poset category of N. You remember I denote omega k to be the poset category of N to the power k. So omega 1 just means the poset category of N. So the objects are natural numbers and the morphisms are pair of natural numbers as the name. So from this poset category, you go to the path category of your directed graph E. Then you can realize this infinite path as a functor. For example, you want to know the image of each morphism, right? So here I plus 1 is a morphism. I will map this to EI plus 1. That means the I plus 1 gauge. And if I have a vertex or, for example, object, I will map this to range of EI plus 1. So I'm viewing in this way, right? So not in usual. Then you can easily check that this infinite path is indeed this functor from this category to the category of all finite paths. And this gives us a way of generalizing thing in the level of K graphs. The definition, an infinite path X in a K graph is just a degree preserving functor from, just replace this omega 1 from the one-dimensional setting in your k-dimensional setting. That means omega k to that. This is the definition of an infinite path, and I denote by lambda infinity the set of all. So this will be my topological space. This has a very nice topology, which is locally compact and Hausdorff. And you can also construct a basis for this topology by defining this as the open sets, Z alpha. So if you take any alpha from your K graph lambda, that means it's the morphism. By Z alpha, I mean to say this X is from omega k to lambda, that means it's an infinite path. That's that x0 d alpha is alpha. I think this notation makes sense because 0 d alpha both are in nk, and obviously 0 less than equal to d alpha. That means this pair is a morphism in here, omega k, and I am applying the functor x. So I will get a morphism in lambda having the same degree. And the condition is that it should coincide with the law. So that is something called the cylinder set at alpha. And this forms a basis for a nice topology. This is a locally compact Hausdorff top space with a basis consisting of these sets. And you can also make this compact if you start with a K graph which have finite remaining vertices. So interesting news is that in the world of dynamical systems and preparing groupoid from them, whenever you have a nice topological space, for example, locally compact Hausdorff, and if you can find a group or an inverse semigroups which act on this space, then you can use that action to form a groupoid, right? Here there is a nice action of NK, obviously this is not a group, this is a monoid, but NK has a nice action on this set, lambda infinity by partial, sorry, by global homomorphism. Right. So if you take any P, a K tuple from here, then I'm associating this with map sigma P, which is a local homomorphism of lambda infinity to lambda infinity. That means if you take any infinite path, its elements are infinite paths, right? So if you take any infinite path by this sigma Px, it should be an infinite path. That means you should know the images of morphisms here. So if you take any Mn, you will send it to, initially X send it to Xmn, but now sigma Px will send this Mn to Xm plus P. So everything shifted by. So this gives you an action of Nk on this lambda infinity by local homomorphism. And if you take the Reynolds groupoid for this lambda infinity with this local homomorphism sigma P's P here from Nk, then this will be our required groupoid, which we call we just denote this by G lambda for simplicity. And this is called the infinite path of lambda. And this is also a nice topological groupoid. And I was mentioning about topological groupoid. This is a ample Hausdorff groupoid. And ample means it has ample source of compact open bisections. This set Z alpha beta. You already know about the cylinder sets. So Z alpha beta denotes this collection. Sorry, what I should first give you an idea of how the elements in this groupoid look like. It suffices to just tell about the Reynolds model, but for general audience, I should mention the elements. G lambda is the set of such triples X and minus and Y, where this X and Y are coming from your infinite path space. This N and M are entries, elements in Nk, but the difference may lie in Ck. In general, Ck, such that if you apply an nth shift on this X and the mth shift on this Y, you should have the same. So these are X and Y called shift equivalent infinite paths. So this is the definition of your groupoid, or the elements look like this. Range is the x0 x, sources y and y, composition very obvious in an obvious way. So you can compose when the range will coincide with the source. The range is z0 z and the source is y0 y. That means y should say the z, and that should be xn plus m w if y is set. Otherwise, it is not composed. And you should define inverse y minus x. And then this will be a groupoid, just a discrete one. Then if you consider this type of sets, take alpha beta from unit set of infinite paths. Sorry, not the set of infinite paths, just the paths in the category K graph, such that source of alpha equals to source of beta. Then just continue plugging in infinite paths. So suppose alpha is this, beta is this. I should not draw pictures so easily in the level of K graphs, but for simplicity, I'm doing so. Just you add an infinite tail. Alpha x, T of alpha, minus T of beta. X is an infinite path, so that's the range of x. So this set form a basis for an ample Hausdorff topology. Right. So you have a nice groupoid, and then you can use this groupoid to calculate its homology. You can also get the associated sister algebra, the discrete Gaussian Steinberg algebra, and my result is that if lambda is a rho finite, a graph without sources, then there exists order preserving sets a modulomorphism, moduli morphism phi from the graded homology, this infinite path groupoid, to the graded K theory of its associated Steinberg. It is independent of the field, so I'm not writing field. So in some sense, this is, you can say, it is an discrete and graded analog of Matsui's result. For Matsui, it was just the ordinary homologies, not the graded one. And here there was the C-stretch. I'm just giving the discrete version. For this, I have two proofs. None of them uses those difficult spectrums.
Uses the graph.
Oh, so, yeah.
These versions is for graphs. Matsui.
Yeah, Matsui is one for shapes of finite type that makes sense. Yeah. So that's the higher dimensional generation also. So since I am running out of time, I just want to mention one proof, not both of the proofs, using type seminars. So whenever you have a groupoid, ample groupoid, which it need not be Hausdorff, you can form the type semigroup of this groupoid. It is defined just as the type semigroup of the corresponding Boolean inverse semigroup of all compactable bisections. GA stands for the BIS consisting of compactable bisections. Since you are working with ample groupoids, you have a very natural source of such bisection. So you just consider the type semigroup of this Boolean semigroup, right? Then there is a nice result of our one Osa and Lee, which states that if G is a ample groupoid with a compact unit space, then you have an isomorphism from H0G plus. So you just consider the zeroth homology of the groupoid, take its quadratic form. It's very difficult to define this homology in a little time, but okay, I am assuming that the audience is familiar with this. Otherwise, I do not have any option. H0G plus, this is the positive form of your zeroth homology. From here to the type semigroup of the groupoid. This is a monoid. This is also a monoid. But I should put one more thing, a C here, which stands for the universal abelian cancellative abelian semigroup. Right. So you can perform this construction with any monoid. So this is general thing. If you have a monoid, a commutative monoid, CM stands for this. M, you take the quotient with this relation, which goes like this: x is related to y, x or y are elements of the monoid. If and only if you have A name such that x plus A equals. So you are just creating one cancellation semigroup out of your points. That is called the universal ability cancellation. So it says that if you have a groupoid with a compact unit space, then you have an isomorphism between the positive cone of your homology and the cancellation semigroup. Right, right. But I just checked the proof. It does not depend on this compact. You can replace this with a locally compact unit space. Also, you get the size. So just two more lines. Okay, so in our case, the groupoid is the infinite. But groupoid has a G lambda. Since we are looking for the graded homology, it is just the usual zeroth homology of the skew probe with CK, right? So you have this co-cycle from G lambda to CK, same one triple x and y to same. So there is obvious co-cycle, and this is okay. So just start with the positive form. This result shows that it should be isomorphic with the cancellative abelian semigroup of the type monoid. Right. But in our earlier paper, we realized this type monoid directly from the K group. So there is another result, HMPS. It says that for the infinite path groupoid, G lambda, the type monoid of this Q product coincides with the monoid which we call the talented lambda, right? And nice thing about this talented monoid is that its group completion is the graded K of the strain propagation. Right. So this T lambda, which we directly realize from the K graph, it is very easy to define this T lambda. It is just the graded analog of graph monoids, not the graph monoids. And we have proved this, the isomorphism between this E lambda and the type 7. So just put this here. And best thing is that this T lambda is itself cancelling. So if you just construct the universal cancelling abelian semigroup, it will be the same thing. So that means you have an isomorphism in the level of positive points. Now just take group completion. Then you have this isomorphism. This is the graded zeroth homology of G lambda. So that's one proof using type semigroups. There is another direct proof using the diagonal sum algebra of Steinberg algebra, but because of the type constraint, I'm not going with that. Okay, so I should want to finish with another result. Which somehow gives a flavor of introducing this stuff smelt. So just one theorem. So it says that if you have two K graphs, lambda and omega, both are rho finite without sources, then the following are equivalent. You have this. Which preserves the positive cones, obviously. Then because of that result, you can write the homology, but also is graded G lambda, isomorphic with x0 graded G omega, which also preserves the positive cones. The last thing is very interesting, which associates those vertex matrices. So there exist matrices R is and a K double P such that if you take the product R is, then you get vertex matrix, the pth vertex matrix. If you take the product in reverse order, you will get BP. Okay, I should mention that APs are the vertex matrices of this K graph and BPs of the vertex matrix of this K graph. And another thing is that this matrix R intertwines the basic matrices. So RB, right? I think some of you may be aware of this type of conditions which frequently appear in the study of shift spaces. This is called shift equivalent of matrices with non-negative integer entries, which is the characteristic property of eventual conjugacy in the level of shift spaces. But since we do not have notion like eventual conjugacy or conjugacy in this higher dimensional world, but we can have some conditions using these matrices which perfectly resembles of that shift equivalence conditions. Okay, with this, I want to finish.
Very much. Any comments or questions? Like that case. Oh, sorry.
Is there a classification conjecture?
Yeah,
Like,
we are still working on that, but
Who's paying? No.
but it's very tough because we have already found examples
Oh, I see.
to
It's
non-isomorphic KP algebras having the same graded K groups.
I see, okay, so. I see that.
That should not work in general, but we are looking for some particular classes of K graphs for that. Those type of classification should work. But the best thing about this K groups for the talented monoid is that those properties which are not directly related to those factorizations, it can capture those. For example, the scheme which happens in the level of algebras also hold in the level of scale graphs. The equality with the graded homology. Also, this graded K groups for these K graphs remains invariant under those moves in splitting signification which we have in our hand for K graphs. So it gives you some idea about that in not at least for some classes of K graphs, they should act as an invariant. Okay, let's hope for that. Thank you.